We present Ungar, an open-source library to aid the implementation of direct methods for optimal control. Existing general-purpose nonlinear solvers provide generic interfaces to deal with a wide range of problems. Given a vector of decision variables, they minimize a scalar function subject to a vector-valued function of equality constraints, and one of inequality constraints. While this formulation is remarkably general, real-world systems depend on multiple variables. For example, standard optimal control problems optimize sequences of states and inputs over a discrete time horizon n. Even these formulations abstract important information about the system from the problem. States and inputs have different meanings for different robotic systems. For instance, a quadrotor's state and input are different from those of a radio-controlled car living in a two-dimensional world, and even more so compared to the state and input spaces of a quadruped robot. The more complex the systems, the more involved their descriptions become, and the greater the coding efforts of the programmer. So, how can we efficiently translate high-level nonlinear optimization formulations into code, while considering the low-level specifics of a given system? We propose Ungar, a library that provides expressive tools to map mathematical formulations to C++. To understand how Ungar works, we consider the simplified state and input variables for a quadrotor's optimal control. Ungar allows a one-to-one mapping from mathematical expressions to code. Let P be the three-dimensional position of the drone. Ungar defines such a variable as a const per object, as shown. We can also define unit quaternions. This time, Ungar specifies the unit quaternion space using the implementation-defined constant q. On the whiteboard, we may define the quadrotor's state as stacked position and orientation. Once again, this is easy to do with Ungar using an intuitive syntax. The quadrotor's input is a vector of 4 rotor speeds. Finally, the decision variables of our optimal control problem include all states and all inputs over the discrete time horizon n. The corresponding Ungar code is self-explanatory. Once Ungar variables are created, they can be conveniently used to manipulate data. To do so, we can define a map over the decision variables w. Ungar instantiates an array of doubles, and provides a unique mapping from subvariables of w to subarrays at compile time. To see this, we can reread the lines written so far. Firstly, positions are three-dimensional arrays. Unit quaternions are represented by 4 consecutive doubles. States are stacked positions and orientations, so they are 7-dimensional arrays. Inputs are 4-dimensional arrays. Finally, W consists of n stacked states and n stacked inputs. Given all this information, Ungar automatically generates, at compile time, all necessary getters and setters to manipulate the underlying data. For instance, we can get the input at time step 1, and we can set it to 0 using eigen interfaces. Similarly, we can get the orientation of the drone at time step 2 and set it to the identity quaternion. The real power of Ungar is that any changes in the variable hierarchies are reflected at compile time in the rest of the code, without the user needing to worry about indices. For example, we may model exclusively the drone's orientations. We can also further change the meaning of X by introducing a second drone. In this way, we can easily implement multi-robot controllers. This change modifies the signature of the quaternion getter. Alongside the time step, the user must now specify the index of the robot, 0 in this case. The library also provides a custom nonlinear solver. To define an optimization problem, the user must provide its cost function and its constraints. Then, our solver can optimize an initial guess for the decision variables w. Our implementation requires the derivatives of all the functions involved. To this end, Ungar has interfaces to a popular automatic differentiation library that generates all the required code and compiles it just in time. Using Ungar, we implemented a state-of-the-art model predictive controller for quadrupedal locomotion and a centralized, collaborative locomanipulation controller. Ungar is a project meant for long-term maintenance, so its functionalities will improve and increase over time. We look forward to contributions, so we invite anybody interested to check it out at this QR code.